And there is also another method which we can attribute it as yeah, I think it's noteworthy if I can mention this approach also, that the consistent mass matrix approach. And of course, if we compare this lumped mass matrix and the consistent mass matrix approach, it seems that the accuracy is the consistent mass matrix provide us the better accurate result or the model than the lumped mass matrix. So we will quickly try to look at the consistent matrix method for a bar-element. So there are many number of ways. Yeah, let's quickly consider consistent. So there are different ways available for obtaining the consistent mass matrix. These are generally applicable for virtual work principle, which is of course based on many energy principles, such as the one based on the principle of minimum potential energy for elastic bodies. We have already discussed this sometime, maybe not particularly within this course, but during maybe the vibration forces or other, let's say, maybe your control lessons, you have probably heard about these energy techniques. And usually it is relatively a simple method for deriving element equations. Yeah. When we compare these approaches, one elegant and a more simple approach is provided by this method, D'Alembert's principle. So here what we do is in D'Alembert's principle, we introduce an effective body force known as Xe. Yeah. So using D'Alembert's principle, we introduce an effective body force called capital Xe, such that Xe is equal to rho times U hat double dot. So here the minus sign is due to the fact that the acceleration produces D'Alembert's body forces in the direction opposite the acceleration. And the nodal forces, of course, associated with this particular body force terms are found by the following equation, which I will write it down for sake of completion, 2.14. So we know the body forces can be found by obtaining the volume integral of the shape functions, transpose shape functions, times the effective body forces, dV. So by substituting Xe into this equation, we can obtain the following equation. Yeah. The body force is equal to minus triple integral volume integral is rho times the transposition of the shape function U and double dot dV. 10.2.15. We know that u shape function, the displacement function, can be written as shape function times the displacement vector or the matrix. And the first and the second derivative with respect to time of this function are u, let's call it u hat dot n is a shape function which is time independent, and of course displacement function here, and the second derivative is also n times d hat second derivative. So here d hat single dot and d hat double dot are the nodal velocities and accelerations respectively. So by substituting these values into 10.2.17 equation, or let's say the values obtained from 10.2.17 equation into 10.2.16 to calculate the body forces, we obtain the following equation: 10.2.17 into 10.2.16. Let me see whether I got that right. Yes, we get the body forces apply is equal to the triple integral volume integral times mass density transposition of the shape function times shape function dv multiplied by the acceleration term, which is equal to minus m hat times d double dot hat. So the element mass matrix in this case is defined as the mass density, the transposition of the shape function multiplied by the shape function times dv. And the mass matrix in this case, we can call it the consistent mass matrix. Which is quite accurate than the lumped mass matrix, because we call this consistent mass matrix because it is derived from the shape functions n, which are used to obtain the stiffness matrix simple K. So in general, this mass matrix, M hat matrix, given by this equation 10.2.19 will be a full but a symmetric matrix. So we will now develop a consistent mass matrix for a bar element, which is shown in this in the previous the figure, which we considered by substituting the shape functions corresponding to a bar. So we have the general formulation for consistent mass matrix. We now apply it to a bar where we are interested in obtaining the triple integral. And what are the two shape functions? When we talk about a bar, when we consider a bar, it's n1 corresponds to 1 minus x hat divided by L, n2 corresponds to x hat divided by L, times 1 minus x hat divided by L, x hat divided by L dV. By simplifying, we can obtain, so this is 10.2.20. By simplifying this equation 10.2.20, we can obtain the consistent mass matrix is equal to the mass density is constant, the cross-sectional area is constant. Then what is remaining is the shape function 1 minus x hat divided by L, x hat divided by L times 1 minus x hat divided by L, x hat divided by L dx hat 10 to 21. So yes, so in the next step we can do the multiplication for obtaining a solution for this matrix. Rho A integral 0 to L. When we do the multiplication, we have a 2 by 2 matrix. The first element is 1 minus x hat divided by L. Now it is squared. The second term, 1 minus x hat divided by L times x hat divided by L. And the first element in the second row is 1 minus x hat divided by L times x hat divided by L. Then the last term is this times dx hat. It's 10.2.22. On performing the integration, the consistent mass matrix for a bar element can be obtained or can be represented using this simple equation, rho AL, the volume divided by 6. Now you can see it is quite different from that we obtained from the lumped mass matrix method. Right. So since we have now obtained the consistent mass matrix and also we have discussed the lumped mass matrix method, then it's all about, the next step is all about assembling the element equations to obtain the global equation, and of course then to introduce the corresponding boundary conditions to perform the solution. So when we obtain the global equations, now we know when we assemble the element equations using, let's say, the direct stiffness method and consider the continuity of displacements satisfied at common nodes. And of course, we also have to consider the continuity of acceleration is also satisfied. In other words, when we construct the global equations, the forces applied, we know total forces applied is now the contributions from the internal forces plus whatever the effects caused by the dynamical forces. So yes, so once we have this, when we want to, then we can construct the stiffness matrix, capital K, which is nothing but the assembling process over all the, let's say, elements. We consider all the element stiffness matrices and assemble them. And similarly, for the mass matrix, we have to now consider all the mass matrices corresponding to elements, and we need to assemble them over all the number of elements. Similarly, when we consider forces, the external force applied, or when we apply the boundary conditions, we have to consider all the forces applied on the elements. All right. So now we have found, we have gone through the basic steps on of the concepts of how to incorporate the dynamical forces into the already existing problem, which we have already discussed. And now let's try to look at certain examples to get familiarized with this concept.